this part, we will really learn about what goes on inside a battery, and we'll finish the discussion about the power frame grid and an expanded grid. But don't worry, we won't be using any calculations to explain the function of the battery. For the following part, and to make it easier to understand the interactions, we have split the screen into 3 sections. In the first section, we'll see the operation mode. The second section will show the basic electric diagram, and in the section number 3, we will see the chemical reaction. So let's start. We will start with a fully charged battery, as you can see on the level meter in the operation mode section. In the centre of the electrical diagram, we have the battery, connected to all the electrical consumers on the top, and also connected to the engine with the alternator. In the section for the chemical reaction, we have the positive electrode with the active mass made from lead dioxide, the negative plate with the active mass containing pure lead. Between both plates there is electrolyte made from dilute sulfuric acid. The battery provides power to all electrical consumers while the engine is off. That means the battery is being discharged, as shown in the operation mode window. The electrical energy to support the consumers such as the radio, the fan, the windscreen wipers, comes from the chemical reaction inside the battery, shown in the chemical reaction segment. As there was a lot going on in that animation, let's go through each section to pick up on what happened. As the engine was switched off, all electrical energy to supply the consumers came out of the battery. Consider that we have many control units in a modern vehicle and potentially more than 100 electrical consumers. Some of them we recognise, like the radio, but most of them we're not aware of. It's pretty obvious that all these electrical consumers discharge the battery. In this example, the battery has been heavily discharged. We took about 80% out of the battery. In real life, this should be avoided to ensure the engine will start properly. What happened inside the battery is also very interesting. Due to the chemical reaction during the discharge, both plates, positive and negative, now contain lead sulfate, or PbSO4. At the same time, the concentration of sulfur in the electrolyte decreased. It was common in the past to measure the acid density of each cell during service to determine the status of the battery. Nowadays, most of the available batteries are sealed, so you can't measure the acid density anymore. However, some safety rules have to be observed when working with acid. That's why many employees appreciate that measuring acid density is a thing of the past. It's important to remember that a battery that has been discharged to such a low state is recharged immediately to prevent permanent damage. So let's do that. With the remaining energy, the battery needs to crank the engine in order to make the alternator run to recharge the battery. Once the engine is running, the alternator provides power to the battery and the electrical consumers in the vehicle. While we see the reverse process in the chemical reaction and an increase of acid density in the electrolyte, the battery returns to a good and healthy state of charge. Once the engine is running, the alternator provides charge to the vehicle electrical network to supply all the electrical components, such as the control units, smartphone plugged into the 12-volt socket, and features like lights or windscreen wipers. Since the alternator supplies all the electrical consumers, the power to charge the battery is limited. To understand this, it is crucial to understand what could happen to batteries, especially in the winter time. Imagine that you have a customer who drives around in the winter with the lights on, with the heater turned up full to make the car nice and comfortable. They have the front demister on, they have the rear demister on, and possibly electric seats as well. Now, all these consumers have to share the load with the alternator, and this can lead to a negative charge balance in the battery. And over time, it leads to a lower state of charge for the battery. In our example shown here, the battery has been fully recharged during the driving time. During the subsequent training for start-stop or heavy commercial vehicles, you will hear the term DOD, or depth of discharge. In our example here, we discharge the battery down to 20% remaining capacity, which is equal to 80% depth of discharge. This extensive discharge and subsequent charging of the battery in this example represents an 80% depth of discharge cycle. You might recall that we already touched on cycling in the former module when we talked about cycle life tests in EN. From the chemical perspective, we're back in the initial state with high acid density in the electrolyte, PbSO4 on the positive electrode and pure lead on the negative electrode. Here we're talking about sponge lead. What does it mean? In order to provide high electrical performance, it's important to have a large active surface at the plates. The right level of porosity of the active mass, like a sponge, on both plates ensures this large surface area between the active masses and the electrolyte. In the animation, we can see that the sulfate has now left the negative plate. The negative plate is now returning back to lead. It's important to know that this lead contains an expander to make the lead porous, and it enhances the performance of the battery. If the battery is overheated, say above 60 degrees, this can turn back to a solid block of lead. So it's important that we control the temperature of the battery, and we also control how we charge a battery. Okay, let's wrap up what we've just learned. Charging and discharging of a battery leads to a chemical reaction inside the battery involving the positive and negative electrode and also the electrolyte. Due to wear and tear effects, this process is not endlessly reversible. This is what we usually mean when we're talking about the aging of a battery. High temperatures and heavy cycle use stress the battery and increase attrition of the materials involved in the chemical process. With all this information, we are now able to explain why Varta uses an expanded grid only for its negative plate. The pure lead in the active mass is already a perfect conductor. Therefore, the main objective of the grid is not to carry the electrons, but to be a mechanical support for the plate. Knowing that the active mass of the positive plate is composed of lead dioxide, or PbO2, providing less conductivity, we also understand why the shape of the positive grid is so important to achieve the best battery performance. With this expert knowledge available, you can explain in detail all the benefits associated with the little power frame icon on the battery label. Because the power frame grid is so important for performance and quality, Varta use it in all their batteries. Did you know that in our truck AGM battery we use a power frame grid for both the positive plate and the negative plate? What do you think the reason for this is for? This battery is used for long haul trucks where the drivers spend a long time away from the depot, so they use lots of consumers while they were parked up, such as a fridge, maybe a cooker or a microwave, and a coffee machine. As they discharge the battery, more and more sulfate is deposited on the negative plate. The more and more sulfate there is could make it difficult for the truck to start. With the truck AGM battery having a power frame on the negative plate, this ensures that the truck will start in the morning.